Alrighty then, section P2, day 2, continued, exponents and radicals. So radicals and their properties, guys. If a equals b to the nth power, then b is the nth root of a. Just practicing with some of those words again. Practicing with some of those words. For example, if 8 equals 2 cubed, which we all know, then 2 is said to be the cube root of 8. And you've seen this notation before. Cube root of 8 equals 2. The number 8 in this example is the radicand, and the 3 is called the index of the radical. So words that you need to know and that we will use. All right, so let's start. Properties of radicals. This first one, if you're doing the nth root of a to the m power, you need to know that that's also equivalent to the nth root of a being first. So these are the same. But what the important part is, you could do the nth root of a first and then raise it to the m. So you really want to think about what's easiest for your situation. Think about what would be the easiest if I did not have a calculator. That's what I usually try to think for myself. So for example, if I had the cube root of 8 squared, well, I have options. I could say 8 squared is 64 and then figure out the cube root. Many of you may know that. I'm trying to think about the instance of for always. Well, I think finding the cube root of 8 would be easier first because it's a smaller number, especially without a calculator. So I'm going to say I know that's the equivalent of the cube root of 8 and then squared. So then the cube root of 8 is 2, and 2 squared is 4. Okay, so again, think about what's appropriate for the problem you're trying to do. For problem 2, then, if you're multiplying the same index, right? So the nth root of a times the nth root of b, then it just becomes the nth root of a times b, right? For instance, you guys know that like square roots multiply by square roots, cube roots multiply by cube roots, okay? But they don't interchange without some extra sort of work in there. So on this one, let's say we're doing the square root of 3 times the square root of 7, then we would know that that's the square root of 21. For number 3, next property, same thing with division then, okay? Same index, nth root of a over the nth root of b here would be the same as the nth root of a over b, one big fraction. Okay, so for example, the 40th root of 80 over the 40th root of 5. Now, it would be pretty hard, okay, whether the numbers are nice or not, guys, just because of it being a big number, to figure out the 40th root of 80 and then the 40th root of 5. So the advantage is to know this property backwards and forwards, both directions. That's a whole lot easier to say. That's the 4th root of 80 over 5. And of course, 5 goes into 80 16 times. So now it's the 4th root of 16. And now I'm just asking myself, what number do I multiply by itself 4 times to get 16? And you should be thinking that that is 2. Number 4, if you have an index inside an index, as long as there's no number between them, so notice there's nothing in between there, okay, other than a 1, then they just multiply together. These two indices multiply together. All right, so if you come over to the example, then you would be looking at, let's say, the cube root of the square root of 15. Well, remember the square root is never going to be written, but technically there is a number 2 sitting there, right? Because that's what a square root is. And 3 times 2 is 6, and therefore your final answer would be the 6th root of 15. Okay, next property, number 5, the nth root of a to the n equals a. Well, the index and the exponent should undo each other, okay? Just like if you think about the intermediate step, if you do the square root of 5 and then squared, well, square root of 5 times square root of 5, we all know is 5. Or it would be square root of 5 times square root of 5 is the square root of 25, and that's a perfect square, that's 5. All right, so hopefully you've just got down the shortcut. 6, you need to concentrate a little bit more. Okay, because, and we'll have to practice with this, if n is even and you do the nth root of a to the n, you get the absolute value of a. Versus if n is odd and you take the nth root of a to the n, then you get a back itself. Let's do an example for each of those. So give you one with n being even. So for instance, let's do the square root of negative 12 to the second power. That then is supposed to equal the absolute value of negative 12, and that is equal to 12. Okay, if you just thought of it, so if you're trying to memorize, you want to get that down a little bit, but if you thought of it this way, you could do the negative 12. You got to do the order correctly. Correct first. Negative 12 times negative 12, since it's squared, would be 144, and the square root of 144 is 12. Okay, working a little bit different then if n is odd. So now let's say we're going to do the cube root of negative 12 to the third power. Well, then that property is saying that you get back negative 12. Okay. And then again, that has to do with the even and odd of the powers and whether it ends up with a positive or a negative that we did before on the previous notes. All right, so note, fourth root of 81 equals 3 because exactly what we talked about. What can you multiply 4 times? Its same number, multiply 4 times together gives you 81. So because 3 times 3 times 3 times 3 is 81. Fourth root of negative 81, not a real number, guys, right? Because there's no real number that can be raised to the fourth power to equal a negative 81. Think about it, try it out. You'll never get negative. Again, that's because of that positive exponent, if you were thinking of it in terms of like 3 to the fourth, positive exponent, and here it's because of the index being even. Okay, even exponent, not positive. Okay. All right, simplifying radicals. So let's practice with this. You are either probably comfortable doing perfect squares or a factor tree. And for a while, I'll take either. So let's try to practice with both. I hope you're thinking maybe of this one as 3 that was already in front, and the perfect square that goes into 32 is 16. So if you think of this as 3 times the square root of 16 times the square root of 2, because 16 times 2 is 32, minus, if you think of 50 as a perfect square, the perfect square that goes into it is 25. So square root of 25 times the square root of 2. Okay, the other option, I'll stop here for a moment, is for you to be thinking this. However you learned roots, and we'll just make them make sense here in the next couple of days, is this. 32, if you think of a factor tree for 32, 32 is 2 times 16, so it would be the square root of 2 times the square root of 16. 16 is 4 and 4, so square root of 4 times square root of 4. 4 is 2 times 2, so root 2 times root 2, and this one would also be root 2 times root 2. Right? We'll show you how to get to the final answer, whichever way you are thinking about that. You could do that same thing with 50. Okay. All right, if we continue on though, hopefully you're going to tell me that square root of 16 is 4 times 3 is going to give me 12 root 2 minus the square root of 25 is 5 root 2. All right. And now this one, if we had gone back to here, guys. So this part is, I'm just practicing with your factor tree again. If you saw this as 5 root 2's, okay, then you should be able to tell me that root 2 times root 2, here's a pair, maybe you learned it this way, gives you that back. And then here's a pair. And at this point, I know you've all learned it a little bit differently. Typically, I don't write the roots in a factor tree, and even though technically square root of 4 is the square root of 2 times square root of 2. So I really just look at this as a pair of 2's, and this is a pair of 2's. So I'm going to get 2 times 2, and I'm left with this guy by itself. Hence, this would be the root 2 that's left over. Okay, right there. And then the 2 times the 2 up here from these two would give you the 4 times the 3 that was in the front to give you this 12. Okay, you've got to be a master of whichever way you are comfortable. I promise I'm going to do a lot more examples with them both ways until you're totally comfortable. But pick one way or the other. Go with what you're comfortable with right now, and let's continue on. Okay, at this point, guys, then you would have 12 root 2 minus 5 root 2, and I hope you're going to tell me that that equals 7 root 2. If you're somebody who struggles with that, or you were about to tell me something totally different, maybe put an S at the end of what you are saying. For instance, 12 apples minus 5 apples would be 7 apples. So think of it as 12 root 2's minus 5 root 2's would give you 7 root 2's. Okay, until you're absolutely comfortable with that. Again, I'm modeling exactly what your work should look like for homework, exactly what it should look like for a quiz. Err on the side of showing me more versus less, kind of one step per line, final answer boxed. Okay. All right, so on this one, either, now I'm going to take away the roots. Either you're a factor tree person who right now is thinking of 24 as maybe 2 times 12, and then 12 is 3 times 4, and 4 is 2 times 2. And then if you circle everything at the end of the branches for the factor tree, you would be there. Let me see if that will undo so that I can get you back to where we should be a little bit easier to read. Okay. Hold, please. All right, 4 is 2 times 2. So there we go. Circle everything at the end of the branches. There's what you would be looking at. So really what that means, guys, if you are either doing it that way, or you're going to tell me this is the cube root of, well, I know a perfect cube that goes into 24 is 8. And it would be the cube root of 3, because 8 times 3 is 24. Eventually, we want you to be able to think of that way. However, to make sense of what's really happening when you have roots, this is like the cube root of what the factor tree is telling us. It's really 2 times 2 times 2 times 3, if you put them in order. So 2 times 2 times 2 times 3 times 8x's, right? Because it's x to the 8th. 3, 4, 5, 6, 7, 8. Now you see why you don't want to do this very often, right? Because you got a lot of this to write out. But what you should understand, guys, that this really means to you is the following. When there's a 3 here, it means these numbers come out in groups of 3 if you're a factor tree person. So you need a group of 3 2's, and I don't have any more. I don't have 3 3's, so I can't circle it. Here's a group of 3 x's, a group of 3 x's, and I don't have 3 x's left. Okay, so what that means to you is the ones that are left inside that I didn't circle are going to have to remain in the cube root. And what's in there? There's a 3 and 2 x's. Okay, now as far as these, for every set that you have inside, 1 will come out. Because think about that, guys. 2 times 2 times 2 is 8. And isn't the cube root of 8 2? So for every 3 of them, 1 of those 2's will come out. All right, 2 to the first. And then you've got this one again. Also, that one will bring out 1x, and this one will bring out 1x. So you've got a 2 times an x times an x. And then, of course, you've got to clean them up. So final answer would be 2x squared times the cube root of 3x squared. 2 things. I'm going to amend my answer there real quickly. 2 things that are super important, okay, that students get a little bit lazy on sometimes. 1, make sure your root goes over everything you mean, so you really should extend that a little bit. And 2, make sure you leave enough space in here. Okay, don't go crazy, but leave enough space in there that I can tell it's clearly 2x squared times the cube root, and that I don't read it as 2x to the 23rd times the square root of 3x squared, or something completely different. Okay, so be careful of that, please. On number 3, so we know we've learned in the past square roots cannot be left in a denominator, so we need to rationalize. Now, I could try to always simplify the radical first and then rationalize and then simplify again. I usually just probably do mostly the rationalizing and then simplify at the end. So to get rid of the radical in the bottom of this, or the root, I'm going to multiply by the square root of 15 over the square root of 15, because that's not changing the problem, right? That's just multiplying by 1. We multiply straight across for fractions, so that gives us 3 root 15 over, think about what you just learned, right? Square root of 2 times square root of 2 should just be 2. Square root of 5 times square root of 5 should just be 5. Square root of smiley face times square root of smiley face is smiley face. So square root of 15 times square root of 15 is 15. And now the numbers outside the radical reduce, right? So I'm looking at like the 3 and the 15 reducing to 1/5. That's what I'm thinking without writing it typically, but you can only hear me, you can't see what I'm pointing to, so I have to write that. So my final answer would be square root of 15 over 5. That would be a fully reduced answer with my horizontal fraction bar. There we go. All right, so number 4. Let's come back to 4 after we chat about a couple of things. Okay, so leave yourself room for 4. To simplify radicals in the denominator that are part of a binomial, right? Binomial means 2 terms. Terms are split by plus and minus signs like problem 4 was. You multiply by the conjugate. You've all heard that, right? The conjugate. So if you're wondering what we're talking about, don't forget the conjugate just means the opposite sign of the second term. So root A plus root B, the conjugate is root A minus root B. So I have a couple questions, hopefully from Algebra 1, you don't fall for any tricks here. Let me ask you this. Does the square root of A plus the square root of B equal the square root of A plus B? I hope your answer is a big, fat no. Absolutely not. I think if you think they go together, remember the operation that would have to be between them, guys, for them to actually go together would be a multiplication or a division, not an addition or a subtraction. Okay, so be careful, don't fall for that trick. Secondly, I would like to know, does the square root of x squared plus y squared equal just x plus y? And I hope, once again, you're going to tell me a big, fat no, 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 no. Okay? Again, that would be a true kind of operation, guys, if it were being multiplied. If it was x squared and y squared, and you were taking the square root of it and they were multiplied, then you could start thinking about, well, I'm taking an even power of an even root and so on and so forth, and would it simplify that way? Okay, but addition and subtraction are a different animal, all right? So then, now that we have seen this, let's go back to here, and what I'll say to you is, anytime you especially see 1 or especially 2 radicals, okay, think of multiplying by a conjugate, all right? Think of multiplying by the conjugate. And here's what we mean by that. The conjugate of this is root 2 minus root 6, like we just said. You know whatever I multiply by on the bottom, or the denominator, I've got to do in the numerator, right? So that I'm really only multiplying by 1, because they cancel out. All right, so here we go for simplifying then. I'm going to have 3 times this quantity of root 2 minus root 6. You might as well just leave the 3 in the front, because we're trying to simplify this. If you distribute it in, you're probably just going to come right back and factor it back out. So leave it there. You'll decide if you want to put it in later. And then let's go ahead and multiply here. Now you've got a binomial times a binomial, so you're distributing. So you should be thinking root 2 times root 2 is 2. I hope you're thinking outer and inner would cancel, right? Because this would give us negative root 12. This would give us positive root 12, so they're gone. And last term, that one times that one would give us negative, because it's positive times negative, and root 6 times root 6 is 6. So notice, what did that trick do for us? Multiplying by a conjugate, since the middle terms canceled out, right? The outer and inner canceled out, you have no roots in the bottom anymore. So now it's going to be taken care of, no roots in the bottom. All right, continuing down, you've got 3 times root 2 minus root 6. Those don't combine. Over negative 4. We've talked about you can't leave negatives in a denominator. So we will move that up top, right? It's the same as negative 3 root 2 minus root 6 over positive 4. And then, of course, like we've said, your goal is just to get the answer that's in the workbook. So if it's different than yours, could you get to it? Okay, and do you know if yours is right or not? Do you need to ask me a question? I would say for a quiz, you could probably just stop there. The workbook may do this, though, and go ahead and distribute the negative 3 in the top. So as long as you know it would equal negative 3 root 2 plus 3 root 6 all over 4, and nothing reduces there, then you could box that and you are set. Okay. All right, so definition of rational exponents. So if you have a to the 1 over n power, and I'm not positive if you can see that, but that does say 1 over n to the power, then the n is here, guys, and the 1 is there. That's not written. Okay, so that's like a to the 1 over n power. So let's practice. Over here then, you need to realize that 27 to the 1/3, if you were to write that as, since that's a rational exponent, if you were to write that as a radicand, you would write that as the cube root of 27. And what can you multiply 3 times to get 27? That answer would be 3. Okay, got to know these both directions. Then let's do one more. If I was to give you a to the m over n, again, not positive if you can see that, so make that a little darker. Notice the root is always there, and the power is always there. We've already talked about these being interchangeable. Use whichever one makes more sense for your problem that you're working on. In other words, should you put in the root or the power first? So let's practice with one more. If I were to give you 64 to the 2/3, then I want to think of this as the cube root of 64 and make myself a smaller number first without a calculator before I square it, because I really don't want to do 64 squared and then try to figure out the cube root. That's going to be a big number. Again, practice these without a calculator. All right, so the cube root is 64. What do you multiply 3 times by itself to get 64? Hopefully you're telling me 4. And then 4 squared is 16. Okay. If you're struggling at all with which of these, trying to remember which of these is the exponent and which one is the power, or which one is the root, which one's the power, so on and so forth, then these are definitely words to live by. When you're in power, you're on top, and the numerator is the power, okay, or the exponent. And I like to think of roots grow in the ground, they're underneath, and so the denominator is the root or the index, back from those previous examples. Go back and look at those again if that's helpful. Okay, again, the number on top is the power, and the number on the bottom, like tree roots, are the root. Okay.